Let's move on. Linear vector spaces. So we quickly define linear vector spaces and solve some problems. I've set the problems we will deal with. So we'll start by defining what a linear vector space is. Alright. So we say that this right. A linear vector space V. A linear vector space V over a field F of scalars. A linear vector space V, this is just a representation, over a field F of scalars, over a field X of scalars, consists of a linear vector space V over a field F of scalars, consists of vectors x, y, vectors x, y, element of V, such that vectors x, y, element of V, such that number 1, x plus y equal to y plus x. X plus y plus z equal to x plus y plus z. X plus 0 equal to x. X plus minus x equal to 0. How many people? 7. This kind of Alright. So listen please. So we said if you have a linear vector space V, please pay attention. Okay. What do we mean by linear vector space? The one we say a vector space is linear. So I think that a vector space will be considered to be linear, or we say we have a linear vector space if all these axioms, we call them axioms, actually hold for a particular vector space. Please pay attention. You can see a vector space as a set. Okay, just that in this case, this is not the conventional set, where you have just numbers, okay, in the set. So look at this. This is telling you that if you have, so in this case, x is an element of the set, okay, vector space, a set, so to speak. Y is an element of the set, Z is an element of the set, and the set also contains what we call the zero elements, okay? And the property of that zero element is that when I add the zero element to any other element, it will reproduce that element. Is it making sense to you? Okay, and the set will also contain negative of any element. That means if I have any element x, I can also have negative of element x in the set. Okay, such that when I add x and its own negative, I will get 0. And again, we will have it such that when I multiply any element by 1, I'm going to get x. And then if alpha and beta, please listen, over the field K, we said this is going to be representing the field over which we are defining the vector space. This is a field of scalars as we have called it. Okay. In this case, we are calling the elements here, we are calling these ones vectors defined over this field of scalars. What we mean by that, for instance, is if you have a vector, in the normal vectors you are familiar with, let's say you have a vector, let's say 2, 3. This is an example of a vector. Okay? But this vector has been defined over a field. The field, that means the set of scalars that can actually occur here, or with which we can operate this vector, is the set R of real numbers. So this field of scalars will be the field of real numbers or the field of complex numbers, complex number C. Don't forget that all real numbers are complex numbers. This is just taking care of the fact that you can have minus I, you can have I and multiples or coefficients of minus I in the expression in case of complex numbers. Okay, so we have different examples of the vector field. We will go through them one after the other. But basically, we can summarize this as a vector space is a set that preserves addition and scalar multiplication. Okay, I want to believe you have heard of this thing before. There's something we call binary operation. How many of you have heard of binary operation before? Have you heard of binary operation before? Yes. Don't lie. Don't lie against your mother was teacher. Secondary school mother ones. You have heard of binary operation before. When you did binary operation, we were taught things like closure of a set. We were taught things like commutativity, associativity, distributivity. Can you remember that? Yes, sir. You were taught something like the identity element. Can you remember that? Yes. The identity elements, the inverse elements, and all of that. Can you remember that? Okay, so listen out. Binary operations. So listen now, listen. So that's basically what we are saying here. But the operations here that are important to us are addition and scalar multiplication. That means that we want to multiply elements of that set by a scalar if we are carrying out multiplication. So we are interested in addition and scalar multiplication. That means multiplication of the elements of this set, the elements of the vector space, by another scalar. That is what we are considering. And then addition of elements in the vector space itself. Okay, so if it is closed under addition and scalar multiplication, when do you say that an operation is what if a set is closed under an operation? Can you remember those things? No. We say that usually something like an operation star is said to be closed under a set S if for any A, B element of S, A star B is also an element of S. Do you get that? So when you carry out this operation, that's when you pick any two elements in this set and carry out this operation on it, the result is still going to be an element of this set. Does that make sense at all? So when we say a linear vector space is said to be closed under the operation of addition and scalar multiplication, it means that if I add any two elements of the vector space, I should have a result which is also an element of the vector space. Is that clear? When I multiply any elements in that vector space by a scalar in the field over which it is defined, then I should also get an element in the vector space. Does that make sense to you at all? So these are results. So these are axioms of this statement. Do you understand that? Do you understand that? Alright, so you can write now. You can write a linear vector space. So you can write in summary, a linear vector space is one which is closed. A linear vector space is one which is closed under the operations of addition and scalar multiplication. One which is closed under the operation of addition and scalar multiplication. You get that? Alright. So these are implications of that. If it is closed under the operation of addition and scalar multiplication, definitely that means that one of the implications will be if I have x, y to be elements of V, okay, definitely I should have x plus y, to be also an element of V. Is it making sense to you? Did you get this? Did you get that? That means that if I pick any two elements and I carry out this operation on them, I should get these results. Happy? You understand this idea? Yeah. It also means that if I multiply any element, if I multiply x by alpha, where alpha is a scalar in my desired field, then alpha x should also be an element of the vector space. Is it making sense to you? Is it clear? Alright. So these are implications of it, of course. So if that happens, then all of these conditions must hold. So if I want to check if, listen. If I want to establish that a given vector space or a given set constitute a linear vector space, then I will check if it satisfies these conditions. Do you understand what I just said now? I will check if it satisfies these conditions. And if I want to show that it is not a linear vector space, I need to only establish that it breaks one of them. Do you understand what I just said? I just need to find out one of them that it breaks. If I'm able to tell that it actually breaks this particular condition, then it is not a linear vector space. Does it make sense to you? Do you understand this? Alright, so we have examples of this. So let's look at those examples. N tuples space. That's the first example. Example 1, the N tuples space. N tuples space. The N tuples space. Alright. Okay, an example of linear vector space. Here we go. Working example. You get that? This is an example of a linear vector space. So what do we mean by N tuples space? Please pay attention. An example is the space R2. When you see R2, this simply means an n-dimensional set of vectors, okay, containing only real numbers. Okay? So for instance, you have elements of this set to be something like this. You can write them this way, A, comma, B. You get what I just said now? That means that in this case, A will be a real number, B will be a real number. So this is an example of an element of this space. Is it making sense to you? Yes. Okay, you can have a space, let's say R3. This means you are going to have elements like A, B, C. Is it clear? Yes. It can also be written in this form, in form of a closed vector, like A, B, C. It simply means they will contain those three elements like that. Is it making sense to you? Yes, sir. So in this case, because we are dealing with linear vector space, the reason we won't call them sets, so to speak, is that the elements of the space can actually be anything. Do you understand what I just said? The elements can be operators, they can be vectors, they can be matrices. Okay? So they are not necessarily vectors as well. They can actually be actual numbers. Okay? So that's an example. So why I'm calling this a linear vector space, for instance? For instance, if I pick R2, can you show that R2 is actually a linear vector space? It means that we are assuming or we are suggesting that it actually satisfies all these conditions. Okay? Primarily, we are saying that if I pick this, listen now. If I pick any two elements, let's say let x be equal to A, comma B. So this will be an element of the set. Do you understand that? And let y be also equal to, let's say, C, comma B. Is it clear? So it's obvious that x, y are elements of R2. Do you understand that? Okay, so you can check that it actually satisfies all these conditions, for instance. Is it making sense to you? Yes. Do you understand that? Yeah. So if you are asked to show that it is a linear vector space, you will have to check all the conditions. So the first one, you see Roman figure 1, x plus y is equal to y plus x. Roman figure 1, x plus y. So what is x plus y? If you pick the right answer, x plus y will be equal to a comma b plus c comma d. This will be equal to a plus c comma b plus d. Is it clear? Which is the same thing as writing c plus a comma d plus d. Is it clear? Yes, sir. Which is the same thing as writing c comma d plus a comma b. Is it clear? Which is equal to y plus s. So obviously it satisfies the first condition. Is it making sense? Do you understand that? Yes, sir. Alright, so this one is that you are playing around with numbers. Okay, so this one, if you have x plus y, so you can also say let z equal to something else. Let's say z is equal to e comma f, alright? Which is also an element of R2. So you can perform the operation on this. So you can find out, you can establish that x plus y plus z equal to x plus y plus z. Does that make sense to you? Did you get that? Okay. Obviously, the same thing will actually hold. X plus 0, that means it has a 0 element. So the 0 element in this case, we are going to have the 0 element here. The 0 element for our vector space here is going to be when you have 0, 0. Okay? So when you have 0, 0, obviously, when you have this 0 plus x will be equal to what? That will be 0, 0 plus a, b. This will be equal to 0 plus a into 0 plus b, which is going to be a, b, which is going to be equal to x. So that's the 0 elements. Is it making sense? Alright, so you can check every other thing, and then we are defining it over the field R of real numbers. So the scalars we use here are real numbers. So if you use scalars which are real numbers, then you're going to have this to be equal to. So you're going to have this to be the next one, x plus minus x. So number 4, x is equal to a plus b. So obviously minus x is going to be minus a minus b. So if I do x plus minus x, that's going to be equal to a comma b plus minus a comma minus b. That is going to be a plus minus a into b plus minus b. Does it make sense? So basically, we are going to have this thing to be a minus a, which is 0, b minus b, which is 0, which is the same thing as the 0 element. So you can put a bar on this 0 element just to show that, or to suggest that it's a vector. We're dealing with vector spaces, and the elements of the vector space are usually called vectors, even though they may not actually be vectors. You understand that? We call them vectors. They could be matrices, they could be polynomials, and they could be actual numbers, just numbers. Okay, but we call them vectors because they are elements of the vector space. Okay, so that's the 0 element. It's going to give you the 0 element, obviously. So if you check 1 times x, so you can actually basically carry out the order. So in this case, alpha, since we are defining that over the real space, our alpha, beta also will be real numbers. Do you understand that? So that's that about that. So that's an example of a vector space. We have space of number two. So you can play around with the many part of that. Please, let's work fast. Number 2, space of m by n matrices. 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 M by n matrices. So represented as m by n. So if you have a space of m by n matrices, obviously, when you sum any two matrices of the same order, of course you get a matrix of the same order. Do you get what I just said now? Do you understand what I just said? Alright, if you multiply a matrix by a scalar, you will get a matrix too. Do you get what I just said now? So it actually preserves addition and scalar multiplication. It also has a 0 element. For instance, if you do f 3 by 2. That is own 0 element. The 0 element is going to be, in this case you have 3 rows and 2 columns, so you're going to have 0, 0, 0, 0, 0, 0. Is it clear? This is its own 0 element. So for all matrices of order m by n, you're going to have a linear vector space. They constitute a linear vector space. Alright. So another example, example 3. Example 3. Space of functions from a set to a field. Space of functions from a set to a field. Space of functions from a set to a field. So look at it now. For instance, if I define some function f, please pay attention, pay attention. If I define some linear vector space p to be equal to, you know how to define sets normally from MTH 101. Yes. So this is a vector space. Yes, it is a set. So we usually also use the definition as though we are actually defining a set. Alright. So let's say we want to take these to be functions, okay, that actually map or take elements from the real set and use elements of the real set. You get what I just said now? And this is actually a vector space. So it contains elements f, okay, which are functions that take element in the real set and produce element in the real set. Okay. So again, you can actually have for this vector space, you can have a 0 element. For instance, 0 b here will just be equal to, it will be f of any real set, any real number you want to pick here. That will be f equal to 0. You get what I just said now? That means that it will take any element you give it and produce 0. Do you get that? Do you get what I just said now? So that is still a function. Do you understand me? You know, I can say a function f of x is equal to 0. It's just a constant function. It means that if I want to get f of 1, it is 0. If I want to get f of 2, it is 0. And so on and so forth. So it has a 0 element. Okay? And if I have a function, let's say I have a certain function f1, okay, of x, let's say f1 of an element here, let's say the element here is x, plus another function f2 of x. So I can put them together and write f1 plus f2 of x. Do you understand that? It is still another function that it gives you. It should make sense to you. Is it clear? Alright. So the set of so for instance, you can have the set of polynomials or you know, all polynomials over the field of real numbers. If you pick any polynomial, for instance, this is an example of functions like that. If you pick any polynomial, if you sum them, you get a polynomial. If you subtract, you get a polynomial. If you take their negative, you get a polynomial. Do you understand what I'm saying at all? Alright, but look at this. If you have, please listen. Look at this now. You might be given something like this. Yes. No, this is not that number. They are making an illustration. I want to give you okay. Alright, look at this now. So, you may be asked something like this now. Which of them is actually a linear vector space? So, think about this. Which of them do you think is a linear vector space? The first one, the space of polynomial functions over a field f. That means, for instance, consider that you just have arbitrary polynomial functions f1, f2, f3, blah blah blah. Okay, is it possible that if you sum any two, you will always get a polynomial? Abi? You get what I just said? Why is that going to be true? Because in that case, no degree has been specified for the polynomial. Do you understand what I just said? Yes. So if I sum a 1 degree polynomial with another, let's say 5 degree polynomial, I will still get a polynomial. Do you understand that? Whatever order it is. Do you understand what I just said? If I sum 2 5 degree polynomials, I will still get a polynomial, whatever order it is. Is it making sense? If I multiply it by 1, I will still get a polynomial. If I multiply it by 2, I still get a polynomial. Is it clear? So it's quite easy. It's quite easy to see that to actually satisfy all the axioms that we discussed. Okay, but in the case of the second one, the space of polynomials of degree 2. Now, a degree has been specified. That means that, when you say you have a polynomial of degree 2, that means you can have elements like this. Let's say f1 is equal to ax squared plus bx plus, does it make sense? And say you have, let's say, f2 equal to, let's say this one is a1, b1, c1. This one is equal to a2 x squared plus b2x plus c2. Abi? Yes, so, but you know that depending on the values of a1 and a2, it is actually possible that you add these two, for instance, and the square terms will cancel out. Abi? You get what I just said? For instance, you can have f1 to be equal to 2x squared plus 1, and you have f2 to be equal to minus 2x squared minus 3x plus 2. When you add the two, f1 plus f2 is going to be what? This is going to cancel this. Abi? You're going to have at the end of the day minus 3x plus 3, which is not an element of the vector space. Is it making sense? That means this does not preserve addition. Do you get that? It doesn't preserve addition, so it cannot be a linear vector space. Is it making sense? Is it clear? So I told you that to show that something is not a linear vector space, you just need a counter example. Is it clear? Once you are able to produce a counter example, obviously it's not a linear vector space. Is it clear? You get this? The reason for that number 2. Yeah, because it does not preserve addition of elements. I mean, like it's not close under addition. Do you understand that? So if you can sum 2 elements of the set, you can say that. So obviously, in this case, you know that f1 is an element of the vector space, f2 is an element of the vector space, but f1 plus f2 is not an element of the vector space. So that means that it is not a linear vector space. Is it clear? Is this clear? Alright. So that means that if you talk about polynomials, for instance, we are asked about polynomials, you will need to find out if it's just a general and open set of polynomials or space of polynomials without any limitation or no specificity about the degree of the polynomials allowed. Is it clear? Then in that case, you are sure that any polynomials you are, they always get polynomials. Is it making sense to you? So look at the next one. The space of polynomials of degree 2. In this case, a degree has been specified. It could be of degree n, for instance. That means a particular n has been specified. So you will not necessarily get an n degree polynomial when you combine any 2 elements in the set. Alright, so that's that about that. Alright, so we can now solve the problems. Here, the problems, the first set of problems here are examples in the lecture material given to you yesterday. So, alright, look at number 1 question. Let V, are you there? Are you there? No. Are you there? Are you there? Alright. Let V be the set of pairs x, y of real numbers. And let F be the field of real numbers. Define x, y plus x1, y1 to be x plus x1, 0, and C of x, y to be cx, 0. Is V with these operations a vector space? So we want to look at that. You know that normally the way this question, the first part of the question says you have pairs x, y of real numbers. You know that normally you might be tempted to say that it is R2. Do you get what I just said? Okay, but this is not R2. This is a space that you can define this way. For instance, you can say that V contains set of pairs x, y. Okay. So, but now, how do we define these ones? We are now being told that such that when I carry out this operation, x, y plus say x1, y1 is going to be equal to x plus x1, 0. And when I carry out this operation c of x, y, this is going to be equal to c x, 0. Is it making sense? So that's about that. So I can add the conditions so that x, y, of course, are elements of R. Is it making sense? So this is an alternative definition. Is it making sense to you? That means that all the statements you have been given, you may have them in your text written this way, for instance. They actually imply the same thing. Is it clear? Is it clear? That means I have a set which contains elements which are defined in terms of a pair of two real numbers, x, y, such that when I carry out this operation, okay, on any two elements, then this is what I'm going to get from it. And when I multiply by some scalar c, I'm going to get this expression as well. Right. So based on this, we have been asked to establish whether or not this is a vector space. That means here we will check all the conditions of the linear vector space and see if it breaks one of them. Do you understand what I just said? Okay, we'll check all the conditions for linear vector space and see if it breaks one of them. So look at this. What's the first one? The first condition is what? That you should have x plus y to be equal to y plus x. Abi? So you can check that here. If you want to get that, please pay attention, pay attention. In this case, you should not mix them up because x here means an element of the vector space. Okay? Y means an element of the vector space. You know what I just said? It is different from the representation here. This x and y here are used to define particular elements of the vector space. You get what I just said? Okay, so I can say something like this now. I can say let U, V, W be elements of the vector space. Is it making sense to you? Is it clear? Alright, so in this case I can now say, maybe in this case I can write that U is equal to U1, U2, and then V is equal to V1, V2, and then I'll have W to be equal to W1, W2. Do you understand what I'm doing? Okay, your point is that this will be real numbers. Is it clear? This will be real numbers. So this will be real numbers. So in this case, the first one I can find out what V or U plus V will give me. U plus V will be equal to. So don't forget something. I cannot just add here. I have to use the rule given in the definition of the vector space. Does it make sense to you? Alright, so if I have U plus V, that will be equal to U1, U2 plus V1, V2. Does that make sense? Yes. Do you understand this? So this will be equal to what? Based on this rule. When I want to add this, I have to take this one, the first time here, x plus x1. So this will be what? U1 plus V1, sorry. U1 plus V1, the next time is what? 0. It does not depend on this one. It doesn't matter what you have here. This one is going to be 0. Is it clear? Do you understand that? Alright, then the next thing is what? Do V plus U and check if they are equal. V plus U will be V1, V2, okay, plus U1, U2. Is it clear? Is it clear? Okay, so what will this give you? This is going to give us, based on our result again, this will be what? V1 plus U1, 0. Obviously, this is the same thing as what? This is the same thing as U1 plus V1, 0. Okay? Do you understand that? What I have here is the same thing as what I have here. Did you get that? Yeah?
Like you don't feel like you don't stop the condition.
The 0, yes. I got 0. That's the definition here. Can you see? When I want to add this element and this element, I'll pick the first element here, add the first element here, x plus x1. The second one is 0. It does not depend on what I have here. Do you get that? That's what is in the definition. Is it making sense? Do you understand that? It doesn't depend on the definition. So this is what you get from that. You're going to Why am I writing it this way? I want to establish that it is the same thing as this one. Is it clear? Did you get that? I want to see that it is actually the same thing as this. That's why I'm expressing this way. Because V1 plus V1 is the same thing as V1 plus V1. Does that make sense to you? So obviously, U plus V is equal to V plus U. Is it making sense? Do you understand that? So what's the next thing you want to check? What's the next thing you want to check? Okay. What's the second condition? X plus, okay, associativity. X plus Y plus Z is equal to, so you want to check if it is equal to X plus Y plus Z. Alright, so in this case, we're going to be using U, V, W that we have defined instead of X, Y, Z. Is it clear? Alright, so I can find out, that means I want to find out if U plus V plus W is equal to U plus V plus W. Do you understand the idea? So you pick this one, okay, and so add it. Don't forget the addition. You have to follow this rule here. Is it making sense to you? And then when you are done, do this second part too and see if they are equal. Does that make sense? Did you get that?
But Max, sorry now, what I want to ask is that if they give you a question like this, and you know you have this question here, if you not start solving something that they're not broken, you have to solve it to finish.
So that's it. And then if you are able to figure out just by looking at it, if you are able to figure out just by looking at it, I don't worry, by the time we are done with linear vector spaces and linear maps, you'll be able to figure out without solving through all of this. You'll be able to figure out if it actually breaks one of the rules. So you just know the rules and go at the particular rule and go there directly and solve it and move on. You get what I just said? Okay. For instance, now, when looking at this, I should know that if you add, look at something, if you add this thing with any zero element, if you add a zero element with this thing, you should know that it cannot give you x. Is it clear? If you add any element with the zero element, you cannot get the elements back because this one is always going to give you zero. Does it make sense to you at all? Did you get what I just said? So for instance, if you pick u plus 0, you know in this case our zero elements will be equal to 0, 0. So if you want to do u plus 0 elements, what would that be? That's u1, u2 plus 0, 0. Is that clear? Do you understand this? And by this rule, this will be what? This will be equal to u1 plus 0, 0. Is it clear? So this is going to give you u1, 0, which is not equal to u. Is it clear? So obviously it is not a linear vector space. Do you understand that? Because of that singularity, of course, but you might want to walk to that point first before you notice it. But when looking at it, you should be able to notice it, but it's okay you are not able to notice it now because you have not done much of linear algebra. Do you understand this? You get that? Alright. So I need to verify this and the next one. Oh yeah. I'll be back in 2 minutes. I need to verify that and then satisfied.
Oh, I don't know that.
Yes. Remember it's violates. That's when you stop. You get that? You can figure out from the start. You can start with it. You get that? Don't believe that say because it does not satisfy this. Yes. You can figure out by looking at the question that it does not satisfy a particular condition. You can just stop there and write your final result. Is that clear? Is this clear? Alright, so V is not a linear vector space. Alright, so that's that. Okay. Yeah, by the time you get to scalar multiplication, did you notice that? How we notice something here? Please pay attention to this. Look at those 8 conditions we wrote out. If you have observed, you see, please pay attention. Pay attention, please. Sorry, please. Hello, pay attention, please. So listen very well. Hello, listen. These first four actually deal with addition. Can you see that? The first four axioms have to do with addition. You see that? And the last four have to do with scalar multiplication. Do you get that? Okay, so the first one has to do with commutativity for this one. This one has to do with associativity. This one defines the zero element, what we call the identity element. Do you understand that? I remember identity element. If you get, if you add an element with its inverse, it will give you the identity element. Have you now? And if you add the identity element to any element, it produces that element. Is it clear? Alright, so under addition, zero is obviously the identity element. Does it make sense? Alright, so in this case, the identity element under scalar multiplication is 1. Abi? When you multiply 1, or when you multiply, use 1 to multiply any one of them, I'm going to get less that. Alright, and this is what? This is associativity. Abi? Under scalar multiplication. And this is distributivity. So this is what we call left distributive. Do you understand that? And this is right distributivity. So that is it. So these are implications of closure under scalar multiplication. These are implications of closure under addition. Is it very clear? Is it clear? So that's that about that. So let's move on. We're now talking about subspaces. So we have more examples in the there are more examples in the book given to you. So alright, linear subspace. Linear vector subspaces. And just like you have, hello, listen now. Just like when you did vectors, we talked about subsets. Can you remember subsets? Okay. We also have what we call subspaces. That means that if I have a linear vector space, I can have subspaces of the linear vector space. Do you understand what I just said? So the linear vector space, just like sets, if you say something is a subset, that subset is also a set on its own. Do you get what I just said? Do you get what I just said? Okay, for something to be a subset, that means it is also a set. Do you understand what I just said? Alright. It is just that it has been extracted, or it is just some part of a bigger subspace. Is it making sense to you? So for something to be a linear vector space, it also has to be a vector space. Is it clear? Alright, so we look at now the definition of a linear vector space as we come here. Definition of a linear vector space.
What is linear subspace?
Subspace. 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 Look at this. What's subspace? Alright, we can write now. Let B be a vector space. V, that's big V. Let V be a vector space. Let V be a vector space over the field F. Over the field F. Over the field F. Big F. Full stop. A subset W contained by V. You understand this symbol, right?
Subset.
W is a subset of V. Okay? That means V is the one that contains W. Is a subspace of V, a subset W, element of V, is a subspace of V if W is a vector space over F. If W is a vector space over F with operations of vector addition and scalar multiplication on V. With operations of vector addition and scalar multiplication on V. That is somehow abstract. We get more specific. Listen on this. Write in another line. A non-empty subset W of V. Please pay attention. Pay attention. Listen to something. You know that. Please listen. For something to be a linear vector space, you know it has to contain the zero elements. Can you remember that? It has to contain the zero elements. So that means that if I want to have a subspace, you know, unlike subsets, you know, you can have an empty subset. I mean, we used to say that an empty set is a subset of any set. Do you understand what I just said? Okay, but here, you cannot have an empty subspace. Okay, the worst case you can have is the subspace will at least contain the zero elements. Do you understand what I just said? Do you get that? Because it has to contain the zero elements for it to be a space, a linear vector space on its own. Do you understand what I just said? Alright. Okay, so let's move on. So we say specifically a non-empty subset W. That means that anytime we are talking about a subspace, it is usually and always non-empty. Do you understand that? It cannot be empty because it must contain at least the zero elements. Is it making sense to you? Okay, so a non-empty subset W of V, a non-empty subset W of V is a subspace of V. A non-empty subset W of V is a subspace of V. Is a subspace of V if and only if and only if it contains the zero vector, 0V, contains the zero vector 0V, and for each pair of vectors, x, y, element of W, and for each pair of vectors x, y, element of W, and each scalar C, element of F, and each scalar C, element of F, and each scalar C, element of F, the vector Cx plus y is element of W. The vector Cx plus y is element of W. The vector Cx plus y is element of W. So look at this. So we're saying that, listen very well, listen. We're saying that if you have, listen please, if you have W to be a subspace of V, don't forget that it is also itself a linear vector space. So for us to get very specific, it has to satisfy only two conditions. The number one condition, which I said earlier, is the fact that it has to contain the zero elements. Is it clear? That means the zero vector in V must also be present in W. Does that make sense to you? And number two is that for any two elements I pick in W, for any two elements x, y, I pick in W, and I pick the scalar, any element of the scalar field over which it is defined, then this also must be an element of this W. Is it very clear? That means when I multiply this by a scalar and add this to this. So this is just another way to say that it has to preserve scalar multiplication. Scalar multiplication means C multiplied by X, that's scalar multiplication. Then adding it with another element. Okay? This should be element of W. So these two conditions are actually sufficient to establish that the vector space is a subspace of the space V. Right? So actually, it is also sufficient to show that something is a vector space, but we should not use it. We should always use that to actually show that something is a vector space. We are asked to show or prove that it is a subspace. Then these two conditions are what you will need to do. Alright. So let's solve the from the group numbers. The next set of questions. So look at the first one. Let B equal to R3. Can you see that? R3. And W equal to the set containing element X such that X is equal to A into 1, 0, 2 plus B into 1, minus 1, 3, where A and B are real numbers. So is W a subspace of V? Okay, so is W a subspace of so you have been given W to be X such that X is equal to A into 1, 0, 2 plus B into 1, minus 1, 3 and A, B element of R. Right. That's the way we define the space. Obviously, listen now, listen. Obviously, when you put these together, listen very well. When you put these together, hello, listen. When you put this together, basically you are going to have this to be a three-dimensional number. Do you understand what I just said? So any element of this set definitely is going to be an element of R3. Is it very clear? You get what I just said? Okay, when you put this together, it's going to be an element of R3. So it is obvious. I know that this W is a subset of R3. What I want to do, what I want to show now is to find out if it's actually a linear subspace of R3. Is it making sense to you? Do you understand what I just said? So it doesn't have to satisfy so much conditions to be a subset. Do you understand that? Okay. But for it to be a subspace of R3, it has to satisfy these two conditions. Number one is that I want to find out if the zero element is present in W. Is it very clear? That means, listen now. So look at the way W has been defined. We know that W will be equal to, of course, A, B will be any real number. So that means that I want to ask myself that can I have real numbers such that at the end of the day I'm going to get the zero element, okay, in R3. So I know the zero element in R3 is going to be 0, 0, 0. Is it making sense to you? You get that? And definitely I can get this from W. Is it making sense to you? So I know that X. What's the meaning of R3? That's three numbers, Abi? Yeah. So what will be zero element? That will be 0, 0, 0. Abi? So if W is a subspace of R3, it must contain this zero element. Does that make sense? So that's what I want to find out. If it contains the zero element. Is it clear? Alright, so in this case, we're going to have, let's pay attention. So when A is equal to 0 and B equal to 0, you know you can get this from this result. So basically what I have here, I can say this is equal to 0 into 1, 0, 2 plus 0 into 1, minus 1, 3. Does that make sense? Is that clear? If I multiply this by 0, I'm going to get 0, 0, 0. Multiply this by 0, I'm going to get 0, 0, 0. Is it clear? And when I add them, I'm definitely going to get this. Is it making sense? Alright, so obviously, this is what? 0 is a real number. So obviously, the 0 element is also contained in W. Is it very clear? Because W can take, A and B can take any real value. Is it very clear? A and B can be any real value. Is it clear? The 0 element is present. So the next one is what? We want to show that CS plus Y, Abi, is also an element of W. So if we're able to establish this, is it making sense to you? Is that clear? So I can say that x is equal to a into 1, comma 0, comma 2 plus b into 1, comma minus 1, comma 2, and say y is equal to c, comma 1, comma 0, comma 2 plus d into 1, comma minus 1, comma 2. Is it clear? Why is this? Yeah? That's the definition. That's the definition of elements of this space. Is it clear? The elements of this space are defined this way. Okay, this is just like looking abstract. MTH 205. Okay, look at it. Look at it. Look at something. If I want to represent, for instance, if I want to write vectors, look at something. Look at something. If I want to write vectors, normal 3D vectors, you know, how would I represent them? You know, I can see that I have AI plus BJ, Abi, plus ZK. Am I making sense? So I can see that any vector that I have here will be represented this way. Is it clear? Okay, this is a vector. Now listen, this I itself, you know, I itself is a vector. Abi? So I itself, I can say that I simply means I have a unit component in the x direction, 0 in the other direction. Is that making sense? I can say that J means that I have 0 here, 1 here, and 0 here. Is it clear? And K means that I have 0, 0, and 1. Does that make sense? That means any element in this space, I can write it as x equal to a into 1, 0, 0, plus b into 0, 1, 0, plus c into what? 0, 0, 1. Does it make sense to you? Do you understand that? Okay, that's basically what it is. So see this as me trying to get the components of this one. Do you understand that? And the components here. Is it clear? Such that these have to be real numbers. Does it make sense? Alright, so that's basically what we're thinking. Okay, so obviously now this is an element of W. Y is also an element of W. Is it clear? Yes. That's the idea. So we want to find out if we multiply this by a scalar and add it to Y. Will it still be expressible in this form? If it is expressible in this form, then I will know it is also an element of W. Is it very clear? Okay. So it will follow that Cx plus Y will be equal to C multiplying X. This is A into 1, 0, 2 plus B into 1, minus 1, 3. Is it clear? Plus Y. So our Y is now C into 1, 0, 2 plus D into 1, minus 1, 2. Does that make sense? Do you understand that? Alright, so you can simplify this for that. Look at this, look at this. So this is going to give us what? This is going to give us, when I open the bracket and I multiply what's inside, I'm going to have this to be C A into 1, 0, 2 plus CB into 1, minus 1, 3 plus C. Oh, I'm using C on both sides. Let me change this one to D and C. So the C into 1, 0, plus C into 1, minus 1, Is it clear? Alright, so what would this give us now? So basically, I can factorize them. Those that carry, I can add the corresponding components, so to speak. Is it clear? So those carrying these, I can put them together. So let's say I'm going to add this to be CA plus D. Is it clear? Into 1, 0, 2 plus CB plus E into 1, minus 1, 8. Is it clear? So since, listen now, since C is a real number, A is a real number, D is a real number, all of them are real numbers, then it is obvious that CA plus D is also a real number. And what? CB plus E is what? Is a real number. Does that make sense to you? You get that?
Yes.
That's what they need to be for them to be an element of this set. Is it clear? The coefficient of 1, 0, 2 has to be a real number, and the coefficient of 1, minus 1, 3 has to be a real number. Is it clear? Once they are real numbers, then what? They are elements of this set. Is it very clear? So obviously, you can do that one. Therefore, Cx plus y is element of W. Does it make sense? Really? So hence, W is subspace of R. You get that? Yes. Because we have a destination in mind. Because in the definition of the elements of this set, they have expressed them this way. So I want to see if I can get the same expression at the end of the day. So if it matches the definition given at the end of the day, then I'm sure that it is an element of the set. You get it? Look at how is W defined? W means you have a number multiplying this, another number multiplying this. Those two numbers are real. That's exactly what I have. I have a number multiplying this, a number multiplying this. The two of them are real numbers. Is it clear? So definitely they are elements of this. Is it making sense? Alright, now we move on. Let's go there. We have plenty to go Number 3. Alright, number 3, are you there? Let B be equal to R3 and W be defined such that X is equal to X1, X2, 1. Is W a subspace of V? Is W a subspace of V? Without solving anything, can you tell me the answer?
Yes.
How is W a
Subspace of V.
Yes.
It should be a subspace.
Because 0 times that will be 0, 0, 0.
Will you contain elements 0, 0, 0?
Yes.
Yes.
Can you see there now? The third term has to be 1 always. Have you now? So it cannot contain elements 0, 0, 0. So it's not a subspace. That is over inside here. That means that you can't change it. Pay attention. So they said we have R3. Hello, listen now. Out of this R3, we now pick out a subset W which has been defined to contain element X such that X equals X1, X2, 1. Please pay attention. So in this case, obviously, X1 is a variable, X2 is a variable, 1 is a constant. You can't change that thing. Is it clear? That means that for any elements, for any vector that I find, and I want to find out if it's part of this subspace, then I will have to find out if its third term is 1. Is it very clear? Is it clear? Alright, so basically, if I want to find out if it is a subspace of W, I know that 0 in V, 0 vector is 0, 0, 0. You understand that? This one is having its third term to be 0. This one always has its third term to be 1. So definitely, this is not an element of W. Does that make sense? So there's no need to check the second one. It is not a subspace. Is it clear? It is not a subspace of V. This one and next one, they can be any real number. So this one and this one doesn't matter. Actually. Exactly. So that means that one is a single vector. So it's still the same. Yeah. So another thing you can consider is this. So look at another. What if you were given W to be this, W equal to X, so that X is equal to X1, this pay attention, X1, X2, comma, you understand this? Now let's count that out. So the first one, 0 equal to 0, comma, 0, so obviously this is element of W. Let's see, you want to check it, the second condition. Have you seen together? So you want to check the second condition. So you can say what? Let X be equal to X1, X2, comma 0, and Y be equal to Y1, Y2, comma 0. Is it making sense? So we now find out Cx, so Cx will be equal to C into X1, X2, comma 0. This will be equal to Cx1, Cx2, comma 0. Then Cx plus Y will be equal to Cx1, comma Cx2, comma 0. Happy now? Plus Y. Our Y is what? Y1, comma Y2, comma 0. This is going to give us what? It's going to give us Cx1 plus Y1, comma Cx2 plus Y2, comma 0. Is it clear? It's still what? It's still, which is still an element of W. Is it making sense? Because it has a real number A, and the third one is 0. Is it clear? It's still satisfied.
And we put the C outside the bracket.
So you don't be bullied there.
And we put the C outside the bracket.
No, you don't need to put it outside the bracket. What you want to show is that this thing, at the end of the day, it should look like the definition, how the set has been defined. Is it clear? You understand that? That was why we wrote that other one. Okay, I think it's still on the go. That's why we wrote this one. We finalized it this way. I want it to look exactly how the definition is. Is it making sense to you? Do you understand that? So we saw like the definition of W there, they were written as what? A real number multiplying this, another real number multiplying this. So if you can express it in that form, we'll be able to conclude that it's actually an element of W. X1 to X3. So obviously that's not a linear vector space because of the 2 you have here.
What is that?
It will be a linear vector. They can work it out here. I know, no computer can always check. Always check. We have specific cases. Of course, yes, if you have this kind of form, which is not there. But always read the details of the question. Do you understand this? Always read the details.
Why not CX1 plus Y1?
Eh?
Why not CX1 plus
Oh. Can you imagine C was here, C. For you, I think it was a mistake. I thought I mistakenly wrote brackets on this. Actually, when I was done, I thought it was a mistake. Now, C is going to be there. Okay, and I like that thing. Together. What you just make here is that it has to be a real number. You know, I came about the fact that it has to be a real number. The major space is R3. Is it clear? So, if it's a real number, it's still a real number. So, let's move on. Number 4. This one is very simple now. You just have this one does not have I mean this topic now. So this topic has wahala. But this part of the doing does not have Alright, number 4, let's go. Let B equals M22 be a vector space of 2 by 2 matrices, and W equals A22 such that the determinant of A is not 0. Please pay attention. So that means that in this case, we are dealing with a vector space of all 2 by 2 matrices. Abi? We know that that is a linear vector space. It is one of our general examples. Can you remember that? Any m by n matrices, any space of n by n matrices is a linear vector space. Can you remember that? Okay. So that is our V in this case, and then our W has been defined to be a subset such that the determinants of those 2 by 2 matrices are not zero. Is it very clear? That means that out of the set of all 2 by 2 matrices you can think about, and now extract those ones whose determinants will never be zero. Does that make sense to you? And use that to form a subset. Is it clear? So we want to ask ourselves, is this going to give us a, please listen very well, is it going to give us a, what do you call it, a linear vector space? Do you understand that? If it's a linear vector space, that means we want to check that, is it a subspace of the other one? That is, can it on its own form a linear vector space? So we're going to use the same condition, and the first thing you want to check is the zero element. Abi? So what will be the zero element in this case? For a set of 2 by 2 matrices, if V is M22, which is the set of all 2 by 2 matrices, that means the zero element in V is going to be what? 0, 0, 0, 0, 0. Is it clear? Is it an element of this subset W? Is it an element of the subset W? How do you know that? Because its own determinant is 0. And we are looking at a subset whose elements have non-zero determinants. Is it clear? So it does not contain the 0 element. So it is not a subspace of W. Is it clear? Okay.
No, I didn't get that.
Did you get that? No. It is not a subspace of V.
Why?
Look at the definition. W is defined to be the set that contains the matrices, the 2 by 2 matrices, such that the determinant of A is not equal to 0. Did you get that? That means the elements of this subset have to have non-zero determinants. Is that clear? Then the first thing is what? The major space we are given is the space of 2 by 2 matrices. So the 0 element in that space will be this matrix 0, 0, 0, 0. Is it clear? So obviously the determinant of this 0 element is what? Is 0. Is that clear? So since the determinant of this 0 element is 0, then it's not an element of W. Does it make sense? So obviously this implies that what? The 0 is not an element of W. So based on that, we conclude that what? W is not a subspace of V. Is it making sense? Do you get this now? W is not a subspace of V. Number 5. Let B equals C. Let B equals CNN. The n by n matrices of complex numbers. Let W equals n by n Hermitian matrices.
What is Hermitian?
Is W a subspace of V?
You guys know Hermitian.
Yes, for you to answer this question, you have to go Hermitian.
Actually.
But you still do this properly, this course. We still get to matrices and define these kinds of matrices. Look at this. So the sense any n by n matrices. Alright, so the first thing you need to know here is what a Hermitian matrix is. Abi? Alright, so we say that a matrix A is right now. Matrix A is said to be A star is called what do we mean by A star? A star simply means this star. A bar transpose. Listen now. So we usually define the admission for the matrix of complex numbers. That is matrix that have complex elements. And what we mean by A bar means that we're going to take the conjugate. Please listen now. So this A star simply means conjugate transpose. Take the conjugate of the matrix, then you transpose the results. Is it making sense? Alright, so if it happens that when you carry out this operation, it gives you so when they basically satisfy this, listen now, this condition, we say it is admission. Listen very well, listen. So this for this kind of problems, listen, the only thing you need is a counter example. When you get one counter example, that's all. You understand that? So here, don't forget something here. Listen. Unlike the previous question we solved, please pay attention to this. Pay attention to this statement. It says that is W a subspace of V over C. What is C here? Complex numbers. That means our field of scalars can also be a complex number. Does it make sense to you? Our field of scalars, that means if I want to use any scalar to find out if there is preservation of scalar multiplication, then I can pick a complex number. Do you know what I just said? Do you get what I just said? Okay, so unlike previous ones we have done, listen, when they told you that the space was R3, there's no need to tell you over R. You already know it is actually over real numbers. Does it make sense? But in this case, they have told us it is over C, which means that when I want to pick my scalars, for instance, if I want to establish that W is a vector space, and for the second condition I have to use S plus Y, I can take this C to be a complex number. Does it make sense? Because basically C should be elements of whatever field you have defined the vector space over. Does it make sense? Alright, so in this case the vector space has been defined over the field F, which is equal to the space of complex numbers. Does it make sense to you? So I can bring any element of this complex set and actually use it. Is it clear? Is it clear? Alright. So look at this. N by N matrix. That's another problem. You don't know N, Abi. That means that what you want to get to work for any number. Am I making sense? You get what I just said? What you want to get to work for any number. So in this kind of situation, the best thing is to get a counter example. The simplest counter example you can get. And when you see that it actually doesn't satisfy, then you reach your conclusion and move on. Is it making sense? Alright, so for instance, here, if I want to listen. So the zero element in this case for my vector space is going to be an n by n zero matrix. Is it clear? Just like I'm going to have this to be 0, 0, 0, and so on and so forth. Is it making sense to you? Yes, and I have this thing also to be 0, and so on and so forth, up to 0. And I have 0 here, 0, so on and so forth, up to 0, 0. So I can have all of this, 0. I have this also to be 0. Does it make sense to you? Is it clear? Alright, so if I have this, obviously, if I take the conjugate transpose of this, 0 is a complex number. 0 is a complex number with 0 imaginary parts. Is it clear? Alright, so if I take its transpose, it doesn't change anything, it's still equal to this. Does it make sense? If I transpose the conjugate, it still won't change anything. Does it make sense to you? Yes. So obviously, 0 V, when I start it is still going to be equal to 0. That means that what? So this means that 0 is actually an element of our set W. Is it clear? Do you understand that? So that's the first condition. So for the second condition, you want to check. So you want to check that if, please pay attention, if this condition holds for a particular matrix, okay, and we want to find out if we're going to have this expression at the end of the day. For instance, here you can say that it holds for a particular matrix A, and then it holds for another matrix B. Is it clear? So if A, B are elements of W, might want to check if CA plus B, do you understand that? Is an element of W. Is it making sense? That means you're multiplying this by this, and you want to find out if this is going to satisfy that example. Is it clear? Is it making sense? Alright, so now this can be any example. So as done by the lecturer, you just need a counter example to do this. But ideally, if you want to solve this, it's going to take something. But that means that you might want to define something like this. You might want to say that let A be equal to, let's say you want to use a 2 by 2 matrix. Use a 2 by 2 matrix also. You still want to generalize it and see that it actually goes for every other order you want to pick. So that is why it becomes difficult to do this directly from the first question. Is it making sense to you? You get that? Yeah, I mean from the first question, yes. What's that? Anytime you get first question, what comes to your head is letter S. Alright, so an example here, look at something. Look at something now. So a simple example you can use here is you can think of a Amicia matrix, for instance. Think about this. Please listen very well. You can have something like let's say you have something like this. Let's say you have 0 and you have 1 here. Then you have this to be, let's say I and this one to be minus I. Okay? How did we come about this? Listen to something. When you transpose a matrix, so that this leading diagonal element will not change their position. Can you remember that? The leading diagonal element will not change their position. The only one that will change their position will be this. Is it clear? So these are the ones that will be interchanged. Is it clear? So you want to ensure that when you transpose this, you get exactly what you have here. Is it making sense to you? That's how to get an example. For instance, you can also have something like this. You can have 1, 2, and then you have this thing to be 1 plus 2i, and you have this one to be 1 minus 2i. Is it clear? You want to be sure that when I transpose this, I will get this. When I transpose this, I will get this. Is it making sense? When I just transpose. When I take the conjugate of this, I will get this. When I take the conjugate of this, I will get this. Is it making sense? Is it making sense? Okay, these ones will be preserved at the end of the day. So, obviously, when you take, for instance, we say A is equal to this and this is equal to, I'm just trying to let you see how to develop a counter example. I say two. Please pay attention, You want to get A bar. A bar will be equal to 0, this is minus I, this will become plus I, and this will be 1. Does that make sense to you? Is that clear? Conjugate of a complex number. Then when you take the transpose of this conjugate, A bar transpose, that will give you what? You now have 0 minus I, then I 1. Is it clear? Which is the same thing as A. Does it make sense? That's how you can form an example of a Amicia matrix. Is it clear? Did you get that? So you see that if you do the same thing for this, you get that result. Does it make sense?
Oh, yes,
If it's the original result, what is it for? What's that the answer?
This is very important.
Because I'm looking for the original result. Why? I said I'm looking for the original result.
What is it?
You get the conjugate, then the transpose. First get the original result. Why?
That is the definition of a Amicia matrix. Listen. This definition of a Amicia matrix. What we are doing here is to establish whether or not this is going to give us a subspace of V. You get what I'm saying? So, in this case, if you actually want to generalize, make a generalization, like they say A is Amicia and B is Amicia, then you want to establish if when you multiply it by any coefficient, you are going to get W, it will be very cumbersome and almost impossible because you have the field to be the field of complex numbers. You get what I just said now? So it may happen that at the end of the day, depending on the choice of number with which you have multiplied, this may or may not result in an element of the set W. So that is why I said that solve this kind of problem. The counter example is necessary. Do you understand that? The counter example is sufficient. Like I said the other time that if you want to disprove something, you just need one example that shows that it is not reasonable. It does not work. Is it clear? Once you have that example, then that is all. Yeah. Is it clear? This one is 1 minus 0i. Its conjugate will be 1 plus 0i. So it doesn't change anything. Is it making sense? Alright, so obviously for this situation, A star is equal to A. So obviously, A is actually an element of W. Does that make sense? Do you understand this?
Yeah.
So look at this now. So let's see. Equal to I is obviously an element of complex number. You get that? An element of our field. Please pay attention, pay attention. I multiplied by A. Please pay attention, please pay attention. It's going to give us what? It's going to give us I multiplied by 0 into I minus I into 1. So when you multiply this by I, you're going to have what? This will be 0 minus 1, Abi. I times I, that's minus 1. I times I minus 1, negative of it, 1. Then you have this to be 1. Clear? Oh, sorry, I. And listen now, listen. Obviously, this result, if you actually take its transpose, okay, it's conjugate, it's going to give us 0 minus 1, 1 minus I. Is it clear? Do you understand that? Okay, and when you actually transpose that, IA bar transpose is going to give you what? 0 minus 1, 1 minus I.
Don't get it.
That question.
Must be element of W. Does it make sense? Where C is an element of our scalar field. So our scalar field in this case is the complex set. Does it make sense? That means I can pick any element in the complex set and use this to verify if this, this is to check if this condition will hold. Is it clear? Did you get what I just said now? Okay. So that element that I picked here is I. So I is an element of the field F we're interested in, which is a complex set. And if I use I to multiply this element, why am I doing that? Just like I have CA plus any element B. Is it making sense to you? Is it clear? Do you get this? Right. When I do I multiply by A, I'm going to get this result. This is my result. Okay. So I want to find out if this result is a Hermitian matrix. And how do I find out if it is a Hermitian matrix? I will take its conjugates, I will transpose the result, and see if it is equal to what I started with. Does that make sense? So that's what I have done here. Take its conjugates, you will get this result. You know how I think about that, right? Okay, the conjugate of this 0, this is minus 1, this is 2, 1, this is minus I. Is it clear? Is this clear? When I transpose that, I'm going to get 0 minus 1, and this is 1 here, and then minus 1. Is it clear?
No.
Did you get that?
No.
So what I have here is I A star. So obviously this is not what so because I A star is not equal to this, that means that I A not an element of W. Is it clear? Because IA star is not equal to IA, it means that IA is not a Hermitian matrix. Is it clear? Okay.
Jesus.
What's that? Not an element. Oh, not element of W. Yes. Thank you. Not element of W. Do you understand that? In the field over which it is defined. Okay? It is defined over the field of complex number C. I pick a number, I pick a scalar in that field. I pick the number I. I used to multiply a particular vector in the field. And it does not produce a vector in the subspace. That means that subspace is not a linear subspace. Is it clear? That because what we started with the fact that it's going to preserve addition and scalar multiplication. Abi? So I'm multiplying it by a scalar now, and my result is not part of the set. That means that what I have here is not a subspace. Now, if you do IA plus, look at this now, IA plus, let's say the zero element. Zero element is part of W. Abi? You do IA plus zero element, you're still going to get I. Is it clear? You understand that? IA anyway must be a part of this set. Is it very clear? So this is not part of the set. So the thing is this, listen very well. Listen very well to this. That second condition is telling you this. Please listen. So we have the linear vector space V, okay, which is the mother vector space, so to speak. And then we are taking a subspace of it, W, which is a subset of V. We have said one of the first conditions is that the zero element here must also be present here. So the zero element here must be an element of W. We have established that that is true. The next thing is that for any C element of the field, so this has been defined over the field F, of scalars, the field of scalars. So for any scalar and how big in that field, Cx plus y must also be an element of W. C can be what? Any scalar in the field. Is it clear? Do you understand what I just said? So why did I have to pick one scalar in the field? Because I want to counter it that it is not a linear vector space. Is it clear? I want to counter the argument. So I've told you that if you want to prove that something is true, you have to prove rigorously using the first principle. But if you want to show that it is not true, you just need a counter example. With the counter example, if it doesn't satisfy that counter example, definitely it is not true. Is it making sense to you? Do you get what I just said now? Alright, so if I say everyone in this class, for instance, if I say everyone in this class offers maybe MTH 104, for me to prove that that is true, so I need to show you probably the registration record, the registration form, and because registration form of each person, I'll show you, okay, this is MTH 104 in each of them. Is it clear? In that case, I need to convince myself that it is applicable generally. Do you understand that? But if I want to show that it is false, I just need to pick one person that is not offering MTH 104. Once I show that this person is not offering MTH 104, then I have established that that statement is false. Is it making sense to you? Do you get that? So what we have done here is what we call proof by a counter example. So we have picked this particular set, and I told you that this particular element, I told you how you can come across
We are proud to have you.
elements like this. You understand that? You have this particular element. So the first thing you want to check is you have to pick an element of the set W. That means that whatever A you have picked must be a Hermitian matrix. Is it clear? Is it making sense to you? So we have seen that this is a Hermitian matrix. That means A is an element of W. Is it clear? Then I went ahead to pick C. So don't forget that in this case, our scalar field over which we have defined the set or the space is the set of complex numbers C. That means I can use any complex number C. When I use any complex number C to multiply that element, it should give me an element of the subset. Is it making sense to you? If it does not give it, then I've achieved my aim. I want to give a counter example. Is it clear? Did you get what I just said now? So I have picked I. So I is what I have picked here because it is an element of our field of scalars. Is it clear? So using this,
We are proud.
using this to multiply A, we got this result. Is it clear? Then for this result, we just need to show that it is not a Hermitian matrix. If it is not a Hermitian matrix, then it has defaulted the conditions. Yeah. Number 6. Let A be an element of M, which is n by n square matrices, and show that this set W, which is a subset of M n1 of all solutions of A n by n x n by 1 equal to 0 n by 1 is a subspace of n1 n by n matrices, and we want to show that the set W, which is a subset of n1. So this means that you have an n by 1 matrix. Is it clear? That means that W will contain elements which are n by 1 matrices. Okay? And you want to show that for this, there are solutions of this equation A n by n multiplied by x n by 1 is equal to 0 n by 1. We want to show that this is a subspace. W is a subspace of this. So this requires some things you have learned in the past. Please pay attention this class. In MTH 101, we were taught solutions to linear equations. So let's quickly revise that. You have something like this: A1, something like A1x plus B1y plus C1z equals to 0. A2x plus B2y plus C2z equals to 0. We have something like A3x plus B3y plus C3z equals to 0. Please pay attention, please. Now, when you don't have 0 here, you know you can have constants like, say you have constants D1, D2, D3. Do you understand that? Okay, in that case, you say that. Listen, please. You have a set of linear equations in terms of x, y, and z, okay, which you can solve simultaneously. You can use the matrix method, or you call the Cramer's rule, and all of that to get this result. But when you have the results here, listen now, when you have the numbers outside here to be all zeros, then there's another problem. You know the problem here is that you cannot use Cramer's rule. Because if you want to get the determinants, any of the determinants that should be at the denominator will carry 0. Do you understand what I just said now? You're going to be getting 0 determinant all through. Is it making sense? Which means that if you use that, you're going to get just a simple result. You're going to get a single result, which will be 0, 0, 0. X equal to 0, y equal to 0, z equal to 0. Which may not necessarily be correct. Do you understand what I'm saying? Okay, so if you want to deal with this, listen now. So this is a case where I have 3 elements and 3 equations. So I can put this in matrix form. I'm going to have A1, B1, C1, A2, B2, C2. I'm going to have this to be A3, B3, C3, B2, X, Y, Z is equal to 0, 0, 0. So basically what I have here is what? What I have here is a 3 by 3 matrix. Okay, multiplying X, which is actually 3 by 1. And it is giving me 0, which is also 3 by 1. Is it clear? So this is a general case of that right here. So I'm generalizing that if you have a homogeneous linear equation of this form, now it doesn't necessarily have to have 3 unknowns. You can have any number of unknowns. It could be 2, it could be 3, 4, 5, 6, and so on and so forth. Do you understand this idea? Okay? So this will be the general expression for them. You can see that what I have here is what? N by n. So because I have only 3 variables, this is a 3 by 3 matrix. Multiplying a 3 by 1 matrix should give me a 0 matrix of order 3 by 1. Does it make sense to you? So you should know the properties of the general solutions of this. Listen, anytime you have, please pay attention now. Anytime you have a homogeneous linear equation of this form, it has what we call a trivial solution. You should remember this from your MTH 101. Trivial solution means that x equal to 0, y equal to 0, z equal to 0. It's always a solution of the set of equations. Is it clear? It is one of the solutions, always. Okay, so that means you should have this thing to be what? That means I should have, of course, if you say x equal to 0, y equal to 0, z equal to 0, obviously it's going to satisfy all of them. Is it making sense to you? So definitely this is going to have 0, a, comma, 0. That means that in this case, I can have my x 3, 1 to be equal to 0, 0, 0. Because, of course, when I multiply this by 0, 0, 0, to give me what I have on this side. Does it make sense to you? Alright, so you can generalize this for an n by n matrix. If you want to generalize this for an n by n matrix, basically what this is telling you is that you have, please pay attention, you have something like this. You have something like A1, A2, blah blah blah, up to AN this way. Clear? This will be the general n by n matrix. Does it make sense? Then I can multiply it by this. This will be x, x1, x2, blah blah blah. This is our definition. This is our definition of this. Is it clear? So the solutions of this, please pay attention now. So the solutions of this will be that. Pay attention, please. So the first thing is that I know that W contains the solutions to this equation. Now, for W to be a subspace, it first has to contain the 0 elements. Have you now? You get what I just said now? So what is the 0 element in this case? What is the 0 element under n by 1 matrix? So I know that 0 under m, which is n by 1, is going to be this matrix, which is 0, 0, 0, and so on and so forth, 0 in n places. Is it making sense? Is that clear? So I know that this element is a solution of this set of equations. So that means this element is also present in W, because W is a space that contains the solutions to this equation. Does it make sense to you? Did you get that? We are saying that for this kind of equation, what are the solutions to this equation? One of the solutions we know is x1 equal to 0, x2 equal to 0, x3 equal to 0, everything equal to 0. Abi? That is the 0 n by 1 matrix. Is it clear? So that means the 0 element for this space is also contained in this subset. Is it clear? Did you get what I just said now? So I can now write that since 0, 0, blah 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 0 is a solution. The solution, also called the trivial solution of this equation. You are not part of this one. Don't worry, this is the last one. The others are from those ones are quite. This is what this first statement means. It's telling you that A is an n by n matrix. The next one we want to check is what? The second condition. Is it making sense? Is it clear?